How do we denote laboratory or field measurements of sound isolation? When you look at data sheets from different manufacturers, you will typically see something like this when we're talking about airborne sound reduction. It's denoted by the letter R and a W, which stands for reduction, and the W is weighted because the sound reduction of a building element, could be a wall or a window or a door, is different for different frequencies. Certain frequencies will have an easier time to get through, whereas other will be effectively stopped by the construction. So that's why there's a W there. It's a weighting. We look at all these different frequencies and we weight them into one single number quantity, and that's a single number quantity which is called RW, for instance. Now, when it's denoted like this, then it means that this is a laboratory measurement. And then sometimes when you look, you can find measures that are denoted like this, R prime W. And this is to indicate that this is field value. So what's the difference between a laboratory and a field measurement? Well, if you make a measurement of a wall construction in a laboratory, you will have like a concrete bunker, which is infinite sound insulation. All the transmission paths over the surrounding constructions in the flanks, except for an opening between two rooms where you construct your wall sample or floor sample. So all the sound that you can measure in the sound reduction will go directly through the separating construction. So in the laboratory, you're only measuring your wall or your door or whatever it is. It's only this single element. But when you take the case in the field, and you take this wall, which measured, oh sorry, it's just my washing machine reminder. So if you take the wall, which perhaps measured 55 dB sound reduction in the laboratory, and you put this wall between two rooms in the field, you will not get 55 dB in the field. Because in the field, you will have several transmission paths. And the primary difference between the lab and the field is that you will have flanking transmission. You will have sound that will travel. Let's see if we can paint this in a good way. If we do the laboratory setup, we have like two rooms like this. And it's infinite sound reduction through the flanks in this one. So you only measure what goes straight through the wall here. Let's say there's a little opening here. And this is your wall sample. Here you build the construction that you want to test. And then the sound that is transmitted through the flanks like this, there's nothing left on the other side because it's so high flanking sound isolation in this case. However, if this would have been the finished building in the field, then you will have your two rooms like this. Maybe you have apartment 1 and you have apartment 2 here. And you build this 55 dB wall. And then you will have your 55 dB sound reduction straight through the wall. But you will also have flanking transmission. Some sound is going to go down into the floor structure. And it will travel in here and excite the floor in here and radiate sound that path. So now you have two transmission paths. And the same goes for the ceiling. It's going to go, some of the sound is going to go here and excite the ceiling too. So you get another transmission path there. And this is when we look at it from the side. We could look at it from the top and you will get the same thing with the walls. If I draw a little window here, you can clearly see that it's so. Now there can be no doubt that this is section drawing. It's from the side. But you will also have flank that will go into this. It's an outer wall because there's a window here. Wall-to-wall transmission. So there's going to be many different transmission paths. All the flanking constructions will transmit sound. And the more sound transmission paths that you add up, the lower the total sound reduction is going to be. And that's why you will always have a lower value in the field compared to what you can measure in the laboratory. And this is good to know. So if you see these, now you know why there are two of them. If you get the prime sign here, it's a field, and this one is including flanking transmission. Whereas this one is not. This is only direct. Transmission. And of course you have some ventilation ducts as well, which could transmit some sound. You could have some workmanship errors. There might be some little mistakes here and there that will make the situation even worse. Whereas typically if a manufacturer goes to a laboratory, they will probably do a good job when they mount their test specimen into this opening, so that it's going to be a really good measurement and no mistakes. But in the field, things happen, and that's just the way that life is. And in today's video, I'm wearing my favorite green jacket with a white and gray shirt, and then I found this cool little pocket square, which I think did a great match. Burgundy reddish color with a pair of gray lines. Actually, this pocket square it's only burgundy and gray, so it's quite laid back, but I kind of like this combination. I think it goes well with the green, and it's also picks up the shirt in a good way. Oh no, it's a bad fold. The little washing. Maybe I should cut this one away. It's not like you ever wash these guys anyways. So no, doesn't matter. So gray, burgundy. You pick up the shirt in the pocket square, and I also have pants in a similar color. So that's a good tip. Harmonize your outfit so that the colors come back every once in a while in different pieces of garment. It's a good idea. Now I could, for instance, have worn a pair of socks as well with burgundy to pick this one up. I'm not doing it right now, actually. I'm cheating because I have warm socks because it's very cold here in my town tonight. And they're not beautiful, but they're nice anyway. Okay, see you guys later.